Today we're looking at exponential graphs. Now, exponential functions have got this basic form y equals something to the power of x. So we've already looked at parabolas, which were y equals x to the power of something. Notice here that the x is up in the power, it's not down there in the base. Now, what is a? Well, a is just some positive constant. So in this course, a will always be a positive number. And what is a constant? Well, it's just literally a number, 2, 3, 4, 5, something like that. Although it could also be a fraction, something between 0 and 1, like say a half or a third, and we'll look at examples like that in a moment. So a simple example, y equals 2 to the power of x. Every time we say, well, let's let x take a different value, and I've drawn up a table of values here just so that we can see how we build the basic curve of y equals 2 to the power of x. We're basically just raising 2 to the power of something and seeing what we get. So let's ignore the negative numbers for a moment. If we just start by saying let's let x be 0, then 2 to the power of 0 is 1. So this forms our y-intercept here, and I've written anything raised to the power of 0 is always 1. So actually when x is 0, for any exponential graph of this form, no matter what a is, this could be 2, 3, 4, or anything else, a half, even a third, any positive constant, every time we raise something to the power of 0, we get 1. And so that means that when x is 0, y is 1, and that gives us this y-intercept of 1 in any exponential graph of this form. But moving along to the right, if we say what's 2 to the power of 1, well, 2 to the power of 1 is just 2. So here I'm raising 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 squared is 4, 2 to the power of 3, that's 2 times 2 times 2, that's 8. Now, I've included 100 here just to give us a bit of a basis for comparison. Now, 2 to the power of 100 is a massive number. Like, it's phenomenally huge. So if you had 2 to the power of 100 grains of rice, that would weigh as much as the Earth. So this number is truly, truly massive. And you get there only going along relatively not very far. Once we're on 100 on the x-axis, we're up at this giant, giant number on the y-axis. So to say that this curve becomes increasingly steep as you go to the right is something of a massive understatement. It gets really steep. And you can see that even just from here, going 1, 2, 4, 8, these numbers are doubling. So the next number 4 would go with 16, 5 would go with 32. It gets steep really fast, but it keeps on getting massively steep. Now, what happens if we go to the left here and we consider what's happening over here? And in fact, what is this red dotted line? Well, we call this an asymptote and we show it as a dotted line. And it basically shows that the curve gets closer and closer to this line, which sits, in this case, right on the x-axis, but it never actually touches it. Now, why doesn't it touch it? Well, if you raise 2 to the power of negative 1, you get a half. So when x is minus 1 here, y is only a half. But 2 to the power of negative 2 is a quarter. 2 to the power of negative 3 is an eighth. So you can see that as the numbers double when you go to the right, they also halve as you go to the left. So if you keep on halving something, it'll get really, really small, but you'll always have something. It'll never actually be 0. So that means y can never be 0 with an equation of this form. And so that's why we have this dotted line here saying that, because the line y equals 0 is the x-axis, this curve is going to approach the x-axis but never actually reach it. So we show that with that dotted line there. Now, if we change a to make it into a slightly bigger number, it's just going to make that curve even steeper. So we've already graphed y equals 2 to the power of x, but if we compare that to y equals 3 to the power of x, you can see that we're saying, well, what's 3 to the power of 0? 1. What's 3 to the power of 1? It's 3. What's 3 to the power of 2, or 3 squared? That's 9. And you can see that as we move to the right here, the numbers get 3 times as bigger instead of just twice as bigger. And as we move to the left, they're only a third of the size instead of being half the size. So when we go to graph this one, you'll notice that it still goes through that same y-intercept, but 1 goes with 3, 2 goes with 9, so we're already way up here, and 3 goes with 27, which is well off my page already. So as I go to graph it, you can see that it's shooting up much more steeply, and that's just from tripling the numbers instead of doubling them each time. And here we've got a third, so it's sitting down below, and 1/9. It's dropping down close to the y-axis even more quickly. So if we were then going to graph y equals 4 to the x, it would sit even closer to the y-axis. Now, when that number a that we're raising to the power of x is a number between 0 and 1, the graph swoops down really sharply instead of going up really sharply. And this is a model of exponential decay. So to take probably the simplest of these sorts of graphs, let's raise a half to the power of x. And what you'll see is we get exactly the same numbers in our table of values, except they're all around the other way. So as we move to the right, the numbers are halving, and that's because we are multiplying by a half another time. Whereas as we move to the left, the numbers are doubling. So we still have our y-intercept at 1. That's because a half to the power of 0 equals 1. And we still have our asymptote on the x-axis because the more we halve our numbers, they'll get smaller and smaller, but they'll never actually reach 0. There'll always be something there. And we get essentially the same graph but flipped around the other way. Remember, our other graph was going up sharply like this on the other side. So this one, y equals 2 to the power of x, and the black one, y equals a half to the power of x. The other thing we need to learn about in this course is what happens when you have a number out the front of the formula. So if we put another number here and we're just calling it k, where k is just a constant, it's just a number, maybe it's 5, maybe it's 10, maybe it's 100, k is multiplied by our a to the x part. So we need to look at what this does. Now, in our original graph we looked at y equals 2 to the x or y equals half to the x, and we can replace that a with any number, remember. Really, the number out the front was just 1, so we didn't bother writing it because 1 multiplied by anything is just itself. So there's a cheeky little k in there that actually just equals 1. So when we vary k and make it bigger or smaller, it doesn't change the basic shape of the graph. It's still going to swoop up sharply if it's exponential growth or swoop down sharply if it's exponential decay. But what it will do is sort of stretch the graph and change the height and the width of it. And it will also change the y-intercept. Now, to think about why that would happen, if we just look at y equals 2 to the power of x here, which we've already considered, and then say, actually, let's graph y equals 5 lots of 2 to the power of x, every single spot on this original graph that we want to investigate, if we just looked at that y value and said, actually make it 5 times that, then you can see why here, instead of the y-intercept being 1, it's now going to be 5. And whatever height this is, it'll now be 5 times bigger. Probably it should be going up even more sharply than what I've drawn to really highlight that. So it's still going to go up sharply, in fact, even more sharply, and it's still going to come swooping down and still have that horizontal asymptote on the y-axis. Sorry, on the x-axis. Over here, I've got a model of exponential decay here. We originally graphed y equals half to the power of x. Now think of just a classic sort of example of when you could come across this sort of situation in nature. They frequently measure half-lives of radioactive isotopes. So if they say, well, plutonium has a certain half-life, what that means is that after a certain number of years, you've got half as much of it as what you had before. So if it's halving every however many years, then it's going to halve again after that same number of years. Then you're looking at, well, every time we sub in x for its half-life, we can see how much of it we've got left. So this is an application that we see all the time using actually a half, because lots of things actually have half-lives. But what if we said, all right, what if we're graphing y equals 10 lots of half to the power of x? Well, any y value that we had on our original black graph there would now be 10 times bigger. So instead of a y-intercept at 1, we'd have a y-intercept at 10. So it could be that you're saying, all right, I've got some radioactive isotope, and at the moment I've got 10 kilograms of it right at the start of my experiment. So when time equals 0, you might say I've got 10 kilos. Now, how much of it am I going to have after one time period has passed? Well, I'm going to have a half to the power of 1. That's a half. And 10 times a half, I'm only going to have 5. And that makes sense. After one time period is gone, I've halved it. After another time period's gone, when you've got 2 on the x-axis, instead of 5, you'd only have 2.5 kilos of whatever it is, or maybe you'd have 1.25 after that. So you can see that something that's halving, it's going to be halving whether we follow this formula or this formula, but this number out the front that we're calling k basically just shows us how much we have at the start.